What is the farthest you have ever been from your home? Have you ever left your state, or your country, or perhaps your planet? Unless you are one of the 644 people who have flown high enough to be considered outside of Earth, you have probably never left our planet. But whether we leave Earth or not, we all have a place in the world that we know better than all the others. Our house, our home. The farther we go from it, the more different things we find, and the more new experiences and opportunities to learn. And when we return, we often come back changed, at least a little. The same goes for humanity. We have our home on the blue planet of the solar system, but leaving home has immensely helped us understand more about Earth and about ourselves. Traveling to the moon immensely advanced aerospace technology and also reflected the political tensions of the Cold War. Getting to know Mars up close with the help of probes has advanced our knowledge of the history of our own planet, reinforcing the importance of asteroid impacts in the history of Earth. Sending a golden record with information about humanity on the Voyager probe forced us to reflect on who we are. Exploring the universe and its mysteries is not just a technological and scientific exercise, but a unique opportunity for reflection and exploration of what it means to be human. And that's why I ask, how far from home can humanity go? How much of the universe can we access and understand, and what will we learn from it?
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
The universe is enormous, but how enormous is it? That's what this video is going to be about. This is the video about the boundaries of our universe. But before knowing the cosmic boundaries of the universe's horizon, we need to understand light. No ship or vehicle with mass can travel faster than light. And this is one of the postulates of Albert Einstein's theory of relativity. And to this day, we have found no evidence that he is wrong. Light is the fastest thing in the universe. No matter where you want to go, light gets there first. And this has an interesting consequence. If light cannot reach a place in a certain time, you will not be able to get there either. You simply cannot move faster than light. The closest star to the Sun is in the Alpha Centauri system, which contains 3 stars that became famous in the book The Three-Body Problem. They are more than 4 light-years away. Sunlight takes a little over 4 years to make this journey, as seen from Earth. So a spacecraft departing from Earth wouldn't be able to get there in 2 years, nor in 3. A spacecraft leaving Earth would take at least, approximately, a little more than about 4 years to reach the nearest star. In other words, there is basically nothing you can do to reach or affect Alpha Centauri within the next few years. Alpha Centauri is unreachable for us within this near future, and we can define this in an even more general way. The places you can visit within a month are all the places that, essentially, a ray of light leaving you can reach in that month. This is, in essence, your future light cone. And it defines all the places in the universe that you have access to. Every object and person in the universe has their own light cone, which theoretically determines which locations in the universe that object will be able to affect. The region where 2 light cones meet is the shared future of 2 people, a place in space and time where the 2 people can meet. And it is possible to reverse this logic and think about the light cone of the past. These are all the places and things from your past that may have affected you. The light cone of your last month includes all the places from which light could have reached you now, traveling for a month or less. You can represent this light cone with a graph. You are at the center of the graph. The vertical axis from bottom to top represents the passage of time, and the horizontal axis represents distances. The slanted lines represent rays of light emanating from you. The region between the rays of light in your future is your future light cone, which are the places you can reach. And behind you is the beam of light from your past, the places that may have affected you in some way. If you want to know what your future or past shared with another person in another place or at another time is, just draw another light cone from another point on the graph. Thinking in terms of light cones is the key to understanding how far we can go. The problem is that the universe won't stay still while we explore it. The universe is in accelerated expansion, increasing in size faster and faster. The distant galaxies are moving away from us, and not only that, they are moving away faster and faster. In 150 million years, more than 99% of the galaxies will be too far away to visit, which, put another way, means they will be outside our future light cone. The fact that the distance between galaxies is always changing makes it difficult to give a numerical answer to how far we can go. Today, traveling a few billion light-years means exploring significant portions of the cosmos. In 12 billion years, the distances to distant galaxies will have doubled. In a few trillion years, traveling billions of light-years will mean traveling through the vacuum of space without encountering anything. What all this means is that to speak meaningfully about cosmic distances, it is necessary to account for the expansion rate of the universe. And the way physicists solve this is by using something called co-moving distances. The true distances in the universe, called proper distances, change with the expansion of the universe. Co-moving distances account for the expansion of the universe, so they are relatively constant. Co-moving distances between galaxies only change due to actual movement of galaxies and not because of the expansion of the universe. Basically, co-moving distances freeze the distance measurements for the universe of today. A galaxy 1 billion light-years away in co-moving distance today will remain approximately that co-moving distance in 100 billion years. Now, the downside is that this freezing of distances distorts speed measurements. In co-moving coordinates, it seems that light slows down in the future and speeds up in the past, which changes the shape of our future light cone, making it no longer a cone but more like a parabola. With co-moving distances, we can talk about the true limits of the universe. And the first limit is called the observable universe horizon, or cosmic horizon. And it is defined by the past light cone, that is, all the places in the universe that have had time to send light rays to Earth. In co-moving coordinates, the past light cone looks like an opening triangle. The past light cone goes back approximately 13.8 billion years, which is the time until the Big Bang, and forms a bubble of 46.4 billion light-years around our planet. All light that reaches any telescope on Earth is part of the observable universe. Every photo you have ever seen of space is a photo of the observable universe. And here, if the universe is only 13.8 billion years old, how did light travel 46.4 billion light-years in that time? This is a consequence of the expansion of the universe. The effective speed of light is affected by the expansion of space itself. It is as if light seemed faster in the past, and that is why it is important to use co-moving distances, because without them, we would have to actively try to compensate for the effects of the expansion, and it would not be easy at all to think about these distances. The distance of 46.4 billion light-years is called the cosmic horizon, and to be precise, no ray of light can reach us from these extreme locations. The universe was opaque in the past, and light signals could not travel. The oldest possible signal would be a gravitational wave, but we have never detected such an ancient gravitational wave. The most distant light ever observed came from the galaxy JD's GS Z13-0, 33 billion light-years away. And in theory, it is possible to observe light from up to 45 billion light-years away, which is the observable universe horizon in practice. The past light cone determines the observable universe, and the future light cone determines the universe that can be affected by our actions, which can be reached even by weak radio waves traveling for billions of light-years. A radio signal emitted today from Earth will eventually reach all the galaxies in the universe that are within a radius of 16.5 billion kilometers from Earth. This is the reachable universe. And with ships close to the speed of light, a human could, in theory at least, reach basically all the galaxies in the reachable universe. Nothing outside this bubble can be reached unless something very serious in physics is wrong. And here comes some bad news. The number of accessible galaxies will decrease. The universe is expanding, and slowly the galaxies will be farther and farther away. Every year, approximately 3 galaxies leave the reachable universe. Even so, we do not need to be in an exaggerated hurry to leave the planet and colonize the universe. In 100 million years, the number of accessible galaxies will have decreased by only 2%. The best strategy to colonize the largest possible region of the universe is to wait until we have the best possible ships. To reach the limits of the reachable universe, one would need to move almost at the speed of light, which is currently impossible. It makes more sense to invest in fast ships before trying to reach stars and other galaxies. If in 100 million years human spacecraft become only 2% faster, it is still worth the wait. Moreover, this would avoid a very uncomfortable and strange scenario in which a first interstellar mission is sent on a journey that will take centuries, only to arrive at its destination and discover that a much faster ship was invented during the trip, and that this ship actually arrived at their destination first. So how can we colonize as much of the reachable universe as possible? A spacefaring civilization seeking to occupy as much of the reachable universe as possible needs ships capable of three things: moving across interstellar distances, transforming matter into energy, and creating more ships capable of these two things. A ship capable of performing these three tasks is called a von Neumann probe. How close is humanity to making such a machine today? Well, let's break it down. Nowadays, humans use chemically propelled ships to move in space. These ships can go very fast in human terms, with speeds on the order of tens of kilometers per second. But that is still very slow for interstellar travel. There are 10 trillion kilometers in a light year, and it is 4 light years to the nearest star. Chemical rockets are not only slow for interstellar travel, but they also burn their fuel too quickly to accelerate for long periods of time. There are two strategies for interstellar travel that seem to work, at least in theory. Powerful ships with extreme acceleration and ships that accelerate gradually but can accelerate for long periods of time. An example of the first strategy would be a nuclear rocket in the style of Project Orion. Such a rocket would use nuclear explosions as a form of propulsion, which is very cool but extremely dangerous. Humanity needs to learn how to cure every type of cancer before putting a flesh and blood human being in a nuclear rocket like this. And the slow acceleration strategy has already been used to some extent in satellites and probes, mainly the idea of ion propulsion. Ions are atoms that have a total electric charge, either negative or positive. And electrically charged particles can be accelerated very efficiently using electric fields. An interstellar ion ship would likely be powered by a nuclear engine similar to that of a nuclear submarine, without needing to explode anything. The energy would last a long time, ideally long enough for the ship to accelerate halfway towards the nearest star, and then decelerate in the final half of the journey. Whether using nuclear explosions or long-term propulsion, such a ship must reach 20% of the speed of light in order to succeed. Enough to travel to Alpha Centauri in about 40 years. Remember that the ship has to break at some point. This is very important. A few decades is not fast on human scales, but it is almost instantaneous on a cosmic scale. And when it reaches the other star, the ship must be able to refuel in some way. The most ideal scenario would be mastering the use of nuclear fusion. Nuclear fission energy is already mastered by humans, but it is less efficient than nuclear fusion. However, fission also needs to use uranium as a base, and uranium is rare in the universe. Nuclear fusion, on the other hand, uses hydrogen and helium as fuel, which are the two most abundant elements in the universe. It is difficult to imagine a more efficient way to expand and spread throughout the cosmos than with ships capable of using nuclear fusion. So, with the fuel issue resolved through nuclear fusion, all that remains is the ability for the ship to replicate itself and build more ships like itself to travel to other stars. There are many stars in our galaxy, hundreds of billions. And there are a few trillion more stars scattered across other galaxies in the accessible universe. It's not possible to directly manufacture that many ships. The most efficient strategy to occupy as much of the universe as possible is to use self-replicating ships. What this means in practice is that humans may start the colonization of space, but it will be robots that finish the job and become the true conquerors of the universe. More precisely, robots with artificial intelligence good enough to make decisions on their own during their mission, and they don't need to be perfect. After all, the strategy of self-replicating ships has a lot of redundancy. Even if only half of the ships succeed in replicating and continuing the mission, that is already good enough. A self-replicating ship moving at 20% of the speed of light and capable of manufacturing other ships at that speed would be able to occupy the galaxy in just a few million years. And this in a conservative scenario, considering that the process of refueling and replication is slow. An intergalactic journey is not much more difficult from a technological standpoint. It is just a change of scale. Perhaps when a replicating ship reached the edge of a galaxy, it would take a slightly longer pause to create an even larger version of itself. A super intergalactic ship capable of carrying incredibly absurd amounts of hydrogen as fuel, enough to move to the nearest galaxy. Or perhaps the ship would build a funnel to collect the sparse hydrogen in intergalactic space, if that were enough to ensure the success of the journey. The distances would be much greater, with intergalactic travel taking up to billions of years. But we have 150 billion years until it becomes impossible to colonize most of the affectable universe. In that time, with replicating ships, humanity would be able to reach everything in the universe that is currently 3 billion light years away from us. Is the universe practically reachable? This is little compared to the observable universe, but it is a lot. Millions of galaxies, hundreds of galaxy clusters, billions of stars, who knows how many planets. But then, is this the end? 3 billion light-years of galaxies and stars? Is that the practical limit of the universe? Realistically, yes. But ignoring the practical limits of the ship, one can go further and find the final limit, the maximally observable universe. This is the combination of the reachable universe with the observable universe. It is what we could see if we colonized the entire observable universe with self-replicating von Neumann probes carrying space telescopes. We will transform all 16.4 billion light-years around us into a gigantic telescope, capable of collecting unprecedented information about the universe. Literally the largest telescope possible according to the laws of physics. And with a telescope like that, it would be possible to see any galaxy that is currently up to 79.4 billion light-years away from Earth. And this is basically the combination of all observable universes, of all the future, of all the stars in the reachable universe. It is the final horizon of the universe. We will be able to see regions of the universe that will only be visible using a very realistic aggressive expansion strategy. And this might be the most frustrating thing about this story. There is a large part of the universe that, in theory, can be seen, can be studied, but that we will never see. And this frustration is not in vain. It points to something, to human curiosity. I want to know, I want to see, I want to live in this enormous universe, to learn what exists in remote, unknown, and even inaccessible corners. Frustration is negative, but it points to something positive. Human curiosity refuses to know limits. But I can't help but find it fascinating that, even with countless stars and potentially habitable planets within these 3 billion light-years, we will still find it insufficient. And some of us will even feel sad for not being able to access the universe as a whole. What is your opinion on this? Will humans ever leave the solar system? Type your thoughts in the comments. Thank you very much and see you next time.